Here's the second video of naming chemical compounds for Unit 3. The first one dealt mainly with the covalent compounds, naming monoatomic atoms, showing you again the diatomic molecules and the monoatomic ions. Now, naming of the monoatomic ions prepares you for the compounds in which we're going to look at in this video. A couple things that we need to make sure that we understand is that all chemical compounds are neutral, meaning they have no charge. This means they have to have the number of positive charges has to equal out the number of negative charges. Therefore, meaning the cations have to equal the anions in some fashion. Now, there's a couple different ways in which this is done. We'll talk about both of them, but there is one method that is easier above all else. It is one that you were probably taught back in 9th grade if you're seeing this as a junior from here. But they also teach the naming all the way up from usually most 9th graders to college freshmen get taught this method because it is the easiest one. When we write a formula for an ionic compound, there are two main steps. You'll notice that we have a lot of just two steps. Let's try to simplify this as much as possible. So again, do not try to simplify this any more than I already have simplified for you. First step is to write the formula for the cation first, followed by the formula for the anion. One of the big things that we need to remember is that we do not put charges in the final formula. There should be no charges in the final formula because the compounds are neutral. So step one would look like this. Where do those charges come from? Well, looking at your periodic table, that's where. Or you can also know that magnesium is in group 2 and therefore forms a positive 2 charge. Or oxygen is in group 16 and therefore forms a negative 2 charge majority of the time, if not solely. So that's where you get that. Sodium sulfide, you see it as the R written there. With a sodium with having a +1 and sulfur having a -2. Both sulfur and oxygen are in the same group, so therefore they form the same anion, whereas sodium and magnesium are not, so they don't form the same one. Sodium is in group 1, so it only forms a +1. That is the best way you can probably learn it if your periodic table does not have the charges. There is a pattern. We've talked about it. We will continue to talk about it with the charges and the groups in which they are in. Step 2 is to insert subscripts to show the number of each ion. If the charges cancel each other out, meaning they add up to 0, don't put a subscript. By just simply writing the element's name indicates that you have one of them there. You do not put a subscript of 1. Just writing the symbol indicates that you have one of them there. If there is more than one polyatomic ion present, meaning that they don't add up, you will have to put the full polyatomic ion in parentheses. And that is important. That is so important because you can a lot of things can go wrong, as I'll indicate when we do a few examples. But that also comes into the better you know which your polyatomic ions are, will allow you to put the parentheses correctly around those polyatomic ions. So second step is inserting those subscripts to show the number of each ion. If the charges add up to 0, nothing is necessary. Then it's just there. So the second step, we see that because the charges of magnesium and oxygen would add up to 0. We do not write any of the subscripts down in there. Instead, magnesium oxide ends up being MgO. Now, sodium sulfide, why do we have 2 sodiums? Why does it take 2 sodiums? Well, if we reason our way through it, it would take 2 sodiums, both with a positive charge, to cancel out the sulfur that has a negative 2 charge. And so if we count up the number of sodiums, 1, 2, we would therefore need to indicate it with the subscript. And we can count just the single 1 sulfur. It works as just saying, well, there's just 1 sulfur. So how do we indicate that? By just writing the element itself. Another method that we do is known as the crisscross method. The crisscross method is an easy way. It's to show the final formula. All the rules stay the same. There is no difference in your rules. You write the formula for the cation, followed by the formula for the anion. So that first rule stays the same. All you have to do is ask yourself, do the charges cancel out? If the charges cancel out, you don't need to worry about the crisscross method. This crisscross method works when the charges don't add up to 0. So when the charges don't add up to 0, that's when you use the crisscross method. Or you can reason your way through it, just like I had done on the previous example. So when we see this here, we see that aluminum oxide has an aluminum that has a positive 3 charge, and oxygen has a negative 2 charge. The crisscross method has us moving those those numbers down. No charges in our final formula. I cannot stress that enough. No charges in the final formula. Some people ask, where do the charges go? I like to play a little bit of fun and say the charges themselves go to a magical place in Never Never Land. Therefore, they are gone forever. They're fictitious and they move away. Realistically, what we really look at this is if we looked at it from the other perspective, from a least common multiple perspective, we would see that what is the least common multiple between 2 and 3, and that would be 6, meaning it would take a total of a positive 6 to equal out 2. So you need actually to have a total of 2 aluminums with a positive 3 charge to cancel out the 3 oxygens each with a negative 2 charge as you're reasoning way through it. Most people don't look at it that way and say, wow, that's really confusing. The crisscross method works best. That is why we just do that, and we just crisscross our numbers and the charges go away. Where? Not a big worry about where they go, just worry about that. That's how you get your final answer. So if we look at another example of copper 1 oxide, the 1 indicates that it has a positive 1 charge. So nice that they put that 1 in there for us. The negative 2 is the charge. The charges don't match up. They don't add up to 0. So what do? We crisscross them. The 2 goes to the copper, and the 1 theoretically is written by the oxygen. But, however, we do not write 1. So we just get rid of it. And therefore, by writing just O for oxygen, we have it. Notice that, again, there are no charges in the final formula. It's super important that we remember there are no charges in that final formula. We have just the numbers themselves. So let's try it out. And we go through this. Calcium, step one is to write, and sulfate is step one is to write the charges as they are written. So we would write or the ions as we have them. Calcium with a positive 2 charge. Sulfate, polyatomic ion. How do I know that it's a polyatomic ion? Well, the fact that it ends in ATE is the first clue that I have that it's a polyatomic ion. So if you don't have the polyatomic ions memorized, look them up. And therefore you can find them on either on the back of our periodic table or in some other fashion of reference. Google does work too, but never always the best thing to use. So instead, I say that SO4 with a negative 2 charge. We can see that the charges cancel out, and because those charges cancel out, we don't have to rewrite the number again. Instead, what we get to do is just write out CaSO4 is our final answer because the charges themselves cancel out. The next example, aluminum oxide. Seen it already, but let's work our way through it. We can see that aluminum on our periodic table has a positive 3 charge, or we can know the fact that it's in group 13. Group 13 forms a positive 3 charge. They're all metals for the most part, except for boron, which is a metalloid. Oxygen has a negative 2 charge. Why, do you ask? Or how do I know that? Because I looked on my periodic table, or I know that it's in group 16, and all group 16 elements have a negative 2 charge. There are some that don't, but again, for our class, all anions or all nonmetals form anions and therefore have a negative charge. And in group 16, for the most part, they all form a negative 2 charge. Our charges do not match up, so we do the crisscross method, and what we see and get as our final answer is aluminum. There are 2 of them, and oxygen now has 3. Pretty straightforward. Iron 3 hypochlorite. Wow, there's a couple weird things that are happening with this one. Iron 3. What does that 3 represent? That means I have an iron 3. That means I have an iron that has a positive 3 charge. But this hypochlorite thing, what's going on with this? Well, it starts with a hypo and ends with an ITE. That means it's a polyatomic ion. You need to either have it memorized or look on the back of your periodic table for my classes. My back of my periodic table has us looking at hypochlorite and going, oh, it is ClO with a negative 1 charge. That whole ClO has a negative 1 charge. There's some bonding that goes into that. We'll worry about bonding in the next unit. Right now, let's just worry about naming these compounds. So when we see that, we can see that our charges do not match up. I have a positive 3 on my iron and a negative 1 on my hypochlorite. Charges don't match up, so I do the crisscross method. I have an iron with the 1 there, but I don't have to write the 1 because just writing Fe indicates that I have one of them there. But I am going to have more than one polyatomic ion. I need to put the whole thing in parentheses. And so I put ClO in parentheses. Outside of that, I write the 3. Now, if I do not put those parentheses there, it's going to look much different. It's going to look like I have 3 oxygen. That's possible. Unfortunately, in this case, though, that can also change the chemistry that we're dealing with. When does that come important? When we do chemical reactions. So therefore, we need to name our compounds correctly so our chemical reactions happen, or in some cases, don't happen. And that's all is important too. So it's important to pay attention to those polyatomic ions. What I have drawn here is ClO3 is chlorate. 8 is different than ite. So this would be incorrect. Next example is barium nitrate, where I have barium has a positive 2 charge. How do I know? It's in group 2, and it's a metal. It's written first. That's how I know it's a metal as well. Nitrate, I know it's a polyatomic ion because it ends in ATE. And therefore, I'd look on the back of my periodic table if I didn't have it memorized and look it up and find that it's NO3 with a negative 1 charge. Do my charges match up? No! So what do? I crisscross. Again, I have 1 barium, so I'll be BA. And now I'm going to have more than 1 polyatomic ion, so I need to put my NO3 inside parentheses. And put the 2 that crisscrossed on the outside of the parentheses. If I didn't put that there, it would look like I had 32 oxygen. Now, it is possible to have 32 oxygen in a compound, just not this one. It requires a lot more carbon. So those parentheses help us out. Now, that 2 gets distributed to the oxygen and to the nitrogen. So there would be a total of 2 nitrogen and 6 oxygen. So 2 times 3 is 6. 2 times 1 is 2. So that's where I get some of those numbers. Now this next one, this last example here, ammonium phosphate. Ammonium is one that is it's written first, so it's a positive. You can search and search and search the periodic table, but you will not find an element on the front of your on front of most periodic tables, ammonium. You have to know that it's a polyatomic ion, or look it up and say, geez, that looks different. I can't find it on the periodic table. And therefore, you need to know that it's NH4 with a positive charge. There's phosphate, which is PO4 with a negative 3 charge. Some of you might be thinking, but I thought all 8s have 3 oxygen. Not all of them do. Be careful. Notice that our previous example up here, we had sulfate having 4 as well. So it does not matter which one. The 8s do not automatically mean 3 oxygen. It has some other naming weird things. Best case for most students, just memorize it. We can do the crisscross method because, again, doesn't match up. So here I see that my ammonium is going to need parentheses. So I put NH4 inside parentheses because if I didn't put it there, it would look like I had 43 hydrogen. Again, some compounds do have 43 hydrogen, just not this one. And it will change a lot. It will be very difficult to balance chemical reactions if you don't know how to name these things right. And balancing chemical reactions is in Unit 4 very soon. The 1 goes to phosphate, so I don't have to write anything. I just write PO4, and I have ammonium phosphate. Now, what do I do when I want to go the other way? When I have a formula and I want to have the name? Well, it's same thing. It's 2 steps. Weird how I would do that to you. You write the name of the ionic compound. There are 2 steps. Write the name of the cation. Now, if it's a transition metal, you need to include the Roman numerals. It was nice of them to do it for us before. Might as well do it, be nice to the next person on the next time around. So it's important to write those Roman numerals. If we're not sure about whether or not it's a transition metal or not, best idea, look it up. So step 1, Ca is for calcium. The Cu is for copper, but I might not be sure what copper it is. Many students will think that it's copper 2 because they see a 2 there. And that might be what you think. We'll investigate that in just a little bit. But let's get back to the second step. Write the name of the anion. Be sure to change the ending to the IDE, such as the example would be calcium oxide. You still have to name it IDE. That kind of helps us indicate that we're dumb naming the compound. So you have calcium oxide. Calcium is not a transition metal, so we didn't have to worry about the Roman numerals. Oxide is not a polyatomic ion. There you go. If your anion is a polyatomic ion, you do not write IDE. You need to keep that there. So if your anion is a polyatomic, don't change the ending to IDE. So what copper do we have here? How do we know? My suggestion is to ask you a couple questions. What is the charge on the sulfate ion? Well, that's -2. That doesn't change. That will be very helpful to us. What is the number written in subscript for the sulfate? Ooh, that looks like a wrong. That should be sulfate. The sulfate ion. Well, there isn't one, because that 4 actually goes to the fact that it's sulfate. There isn't one, meaning a 1 could be written. Well, do the reverse crisscross. That means the 2, if we look in here, the 2 would go to the sulfate. This 1 here that really isn't there but could be written would go to the copper. That's the reverse crisscross method. When we do it that way, we would see that we have copper 1 sulfate. So we have copper 1 sulfate. A lot of this comes, best way to do this is by trial and error. So let's try some out. I have Fe2O3. Hopefully you know from lots of practice that iron is a transition metal. If you're not sure, you should look. Since iron is a transition metal, I am going to need to write parentheses. So I started out. What goes inside those parentheses? Well, I do my reverse crisscross. And I have a 3 goes up to the iron, and a 2 goes to the oxygen. Does that make sense? Should oxygen have a -2? Yes, it should. And therefore, I have iron 3 oxide. The next example, we have Al2S3. Now, when I look at this one, I name the thing. Now, aluminum is really close to the transition metals, but it is not a transition metal. So just because it's close doesn't mean anything. So I do not need to worry about doing the reverse crisscross because it's not a transition metal. And therefore, all I have to do is name aluminum sulfide. Our next example tends to be a conundrum, and we'll look at it in just a second here. Titanium, Ti, is a transition metal. Now, when we look at our transition metals, we can see that they form multiple positive charges. And oxygen is not, and it always forms a -2. If I did my reverse crisscross, I'm going to have some small issues. Because the 2 would go to titanium. There's not a 1, there's a 1 there, hypothetically, and that would go to the oxygen. That doesn't make sense. I can't have an oxygen with a -1 charge. So what's going on? Well, something weird happens. That is, if I have a charge that can be reduced, we do. And it's not something that we purposely do to just confuse chemistry students. It's something that it happens. And so we would look at it and see that that can be reduced when we have it written out, and it would look very silly. And if we of Ti2O4. So what happens is that they reduce it to write out titanium dioxide. But now you might be asking, why are you calling it titanium dioxide? When it actually should be named titanium 4 oxide. This comes down to the idea that there are multiple types of naming. Some names go through what are known as common names, and they're so ingrained into chemists' brains that that's what we call them, even though titanium is a metal and oxygen is a nonmetal. So technicalities would say that it should be named titanium 4 oxide, but the common name is titanium dioxide. And that's what you're going to find the majority of the time. You would probably be wrong by calling it titanium 4 oxide for most chemists, because the common name trumps. Not too many people would look at it. It's like calling water dihydrogen monoxide. Nobody's going to know. So you name it as it is. The next example, we'll get back to one that maybe makes a little bit more sense, is Mn when we have parentheses ClO with the 5 outside. Well, here we go. If you're not sure that Mn is manganese, well, you have to look it up and then find it there. I usually have to look it up just to make sure I'm spelling it correctly. And so when we go through this, we see that it's manganese, and it's a transition metal. So therefore, I need to have parentheses. What goes inside the parentheses? Well, I do my reverse crisscross. And then when I do my reverse crisscross, a 5 goes there, a 1 that's hypothetically goes there, and that makes sense. Whew. Finally, one that comes back to making sense. So I have manganese 5, but now ClO, which one's that? I don't know. It's a polyatomic ion. It's in parentheses. So I need to look it up. I'm going to run out of space here, so I call it hypochlorite. Again, you can either A, have them memorized, or B, well, look it up. The next example, I have CuCl2. Well, it doesn't pay to say those types of things all the time, so instead I say copper. Now, copper is a transition metal, so I need to know which one it is. Cu, the 2 goes to there, reverse crisscross, so it's copper 2. Cl is not a transition, polyatomic ion, so it's just chloride, making life very easy for us. BaNO2 with the 2 outside the parentheses. What's easier to say is that it's barium. It's not a transition metal, so no parentheses. I have a polyatomic ion, NO2. If you don't know what it is, look it up, and you then find that it is nitrite. Now the next one, the last one here, we have Na with the subscript 2, SO4. Some of you will want to try naming each one of those elements by themselves, but you have to be able to recognize, again, you have a polyatomic ion there. And so you have Na, sodium. Is it a transition metal? Nope, it's in group 1. So that 2 came from sulfate anyway, but it doesn't matter because all I write is sulfate. Now that we've named a number of these things, what we've been naming are known for a lot of these are the anhydrous compounds. Some compounds have what are known as hydrated compounds, meaning that water is a part of the crystalline structure, or water of hydration. Some of these compounds are extremely important into our everyday life. If we didn't have them, a lot of you would not have walls on your house. You would just have empty slats where you would be able to see everyone through there, and that wouldn't be nice. So these hydrated compounds are very important, and they have a little bit of naming that is important for us to see or at least make note of. So if you see it, you know what we're talking about. Calcium sulfate is an example of one of them. It exists in a couple different hydrates, and also as its anhydrous. So we see that calcium sulfate, the anhydrous version, a lot of times not necessary to say that it's the anhydrous, but a lot of times if you were asked to make chemical purchases, you do have to pay attention to if you're buying the anhydrous, this hemihydrate, or the dihydrate. So it's important. How do we get a half of a water molecule in there? That's something that we'll talk about in bonding in Unit 3.5. That is very special to ionic compounds, and that there's a half the water molecule is in part of this repeating pattern that makes up part of the crystalline structure that it has. Now, part of this is those little dots should have been risen up to look like little multiplication sounds. Apparently it didn't transfer very well. But usually they would be up in the middle as little multiplication signs. Calcium sulfate dihydrate, or also known as gypsum, is very important to many builders and for a lot of you in your houses. Gypsum or gypsum rock, also known as sheetrock. And it's very important that you have sheetrock up. Otherwise you have to put plaster and or other means, and it just doesn't work out so well for some people. Some people want it, and some people don't. Otherwise, I guess you would just have some empty slats, or when you can put up particle board in whatever it is. But gypsum rock is sheetrock, so there you go. A very important part, and it's important to note that what it is. So we name them as a dihydrate because there's two water molecules. Now, the acids tend to give most students fits. I'm not exactly sure why. There isn't too many rules for them. It's just that they have some different things that happen. If the anion on the acid ends in IDE, such as chloride, you change the ending to ic and add the prefix hydro, so hydrochloric acid. So you have HCl. I had a student many years back that gave me this way of remembering it. Is hydro means no. Oh. Hydro means no O. So if you have a acid that is called hydro blank acid, there's no oxygen present. So it is just the ion. That's probably the best way I have heard to memorize what kind is it. HCl, it's a hydro, there's no oxygen. HBr, hydrobromic, there's no oxygen, so it's hydrobromic. Is the best way of memorizing it, I guess. But hydro means no O. That was, I believe, Becky Kepp gave me that. Now, if the anion it ends in ITE, a lot of times that's going to mean it's a polyatomic ion. You change the ending to OUS. Now, some of these tend to get really weird on how they sound, so it's important that we make sure that that works out right. You still keep the prefix. If there's a prefix for the polyatomic ion, you keep that prefix there, such as the case with hypo, not to be confused with hydro. P versus dro is different because hypochlorite, ClO with the -2 charge, it ends in ITE. You have a hydrogen written first. That's the other telltale sign that it's an acid. The hydrogen's written first, and that you change it to hypochlorous acid. HClO2 is known as chlorous acid because it comes from chlorite. The hydrogen is written first, indicating it's an acid. If the anion ends in ate, if you ate it, it would be icky, and therefore it's an ick acid. Chlorate makes chloric acid, and perchlorate makes perchloric acid. Ates turn to ick. Ates are icky. If we ate it, you found out that it's icky, and that's kind of how we would look at, rhyming or naming scheme to help us name it a little bit better. So again, practice, practice, practice. So let's try some of these out. H2S. Is there an oxygen present? Nope. Because there's no oxygen present, we call it hydro sulfuric acid. Well, I did not write that very well. And so we have that first one. Now, do not confuse hydrosulfuric acid with another very nasty acid of sulfuric acid. Our next one, no, it's an acid because the H is written first, and therefore it's PO4 we need to look at. If we don't have those polyatomic ions memorized, look them up on the back of your periodic table or another reference material. PO4 is phosphate. Eight's turned to ick, and therefore we have phosphoric acid. Now, phosphorus acid, because it ends in OUS, means that it comes from the polyatomic ion to give us the compound H3PO3. Now, where did that 3 come from? Well, if I look at and write out my ions, I have a hydrogen, has to be written first. In this case, because it's written first, has a positive charge. My phosphate, my phosphite. See, even I sometimes get that confused. Phosphite is a PO3 with a -3 charge. If I look, I can see that my charges don't match up. So what do? I do the crisscross method. The crisscross method still works. And so we have H3PO4. Now in the next one, carbonic acid. We'll do the little crisscross here for the beginning. I know it's an acid because it says it, so that means hydrogen's written first. Because hydrogen's written first, it has a positive charge. Carbonic came from, because 8s are icky, it came from CO3, -2 charge. I can see my charges don't match up. I crisscross them, and I write H2CO3. Now, in the last one, next two, we have H2SO4. Now, I need to recognize that SO4 is a polyatomic ion. That means that I have a polyatomic ion. I have oxygen, so it's not hydro. It is just sulfuric acid. Not my favorite acid. I've had some run-ins that have left me scarred, so to speak. Last one here, hydro. Hydro means no O, so I have an H. Fluoric comes from fluorine, so therefore it's HF. Now, if we look at how we do some of the other stuff, it came from H plus F minus. Charges cancel out, giving us just HF as the formula. Made famous by art students making etching in their glass, or the TV show Breaking Bad, which it did not do, does not do the damage that it said it did. Weird how Hollywood got it wrong. The last little bit is some organic chemistry. Some of the common ones that we need to worry about. We'll see that we have methane, ethane, and propane. The difference in them is that they have more carbon as we progress from left to right here. It has its own naming system. Some of these gases and/or organic compounds are going to be extremely important for your everyday life. So naming them is also going to be important. It has its own little scheme. We'll notice that they're all nonmetals, but they don't get named the same. The simplest ones are known as alkanes. Methane, a lot of you would probably want to call it carbon tetrahydride, but that's not what its name is. Its name is methane. Many of you heat your house by it, of methane. And then you have ethane and propane. And yes, that is the famous propane and its byproducts that also many of you might, or some of you might heat your house with. But it's also used for, in many cases, grilling. And we're not going to sit here and debate whether grilling or barbecuing is better for using charcoal or not. It's just giving you the heads up that propane is this. Now, there's some things that happen as you add these carbon and hydrogen to them within their chemistry and their physical properties. We'll talk more about that in the chemical bonding. But what you need to know is that CH4 is not our carbon tetrahydride. It is methane. And ethane is C2H6, propane C3H8. The naming that we do, how do we know that? Meth equals 1, eth equals 2, prop equals 3. There's other ones as well, such as butane, pentane, hexane, heptane, octane. I hope you maybe get the picture of that without me having to draw it, that they have them. Again, you've probably dealt with butane, lighter fluid. So it is there. You name just the first part, and if there's nothing else there, you have the ending of ANE. There's some other stuff that happens if it's all double or single bonds, but again, we'll worry about the bonding issue in the next unit. If they have a important functional group, such as the OH group, which is in organic chemistry known as the alcohol group, and not hydroxide. A lot of you would probably recognize it as the hydroxide from your polyatomic ions. It is known as an alcohol group. It's a functional group. It changes the chemistry that's there. So methane, because it lost a hydrogen, so to speak, and became methanol. And then we have ethanol with, yes, it's the stuff that we put in for E85. That means it's 85% ethanol. And then you have propanol and some of those things. And some of these alcohols are extremely important for our everyday life when it comes to some of the chemistry that we see beyond gasoline additives. As we look forward, that's what we'll look at. This is the end of Unit 3 in chemical names. Again, this was intended to be supplemental for the notes that we have in class. Hopefully, maybe you caught something in class, or maybe this video helped you out as well, and then it did the job that it was intended to do. I hope you enjoyed the videos, and I hope that you use them appropriately to help you study and make the class go that much easier.